Hey, look at you. You came back to chapter 2. We are going to go over sound in this lecture. I'm kind of talking about some of the basics that we need to know about just sound in general. And then the rest of the book really is going to hit those ultrasound physics. So there are 5 things that you need to know about sound. The first one is that sound carries energy. There is energy found within the sound waves. It propagates through different media and it carries that energy through the media. So sound carries energy. Now the second thing is that sound waves are mechanical waves. The energy that they carry is mechanical, meaning that it can move stuff. And that's exactly what it does. It moves particles within media. So sound waves are mechanical. And that brings me to the third thing. Sound waves can only travel through media. There has to be a wall, water, air, a person, a rock, something made of material, something made of particles, so when that sound wave travels through it, it can move those particles around and continue moving forward. So it has to have something to travel through. Now you may have heard the line, "Nobody can hear you scream in space." Technically that would be because space is a vacuum. Vacuums don't have any particles in them, and because of that, sound wouldn't be able to travel through it, so nobody could hear you scream because the sound wave couldn't travel. So again, sound waves can only travel through media. Number 4, sound waves can only travel in a straight line. Now, you know that you can be in one room, yell something to your buddy in another room, and that they can hear it, and it's because it bounces around and echoes. The big thing is, though, is that it doesn't go out the door, turn the corner, and then get to your buddy. No, it hits the wall, bounces off that wall, goes another direction, and then eventually it gets to your friend's ears. So again, sound can only travel in a straight line. It does not curve or bend. And lastly, sound waves are longitudinal waves. We're going to go over what the 2 different types of waves are. They are transverse and longitudinal. All you need to know right now is that sound waves are longitudinal waves. So if you know these 5 things about sound, you are 5 things smarter towards your ultrasound boards, and these are going to help you just to relate back to some physics concepts that we'll talk about, and then we'll actually kind of talk a little bit more about these when we talk about artifacts and how some of these things apply to artifacts. Now there also are some helpful terms that you need to know as we talk through this chapter. And we'll cover them again as we get through the lecture. But the first one that I want to talk about is rarefaction. Rarefaction is when particles are stretched out. The opposite of a rarefaction then is a compression, and a compression are where particles are squeezed together. So when we look at a sound wave, oftentimes you are going to see the wave kind of mapped out like something like this. And we consider compression to be this top part and rarefaction to be this bottom part. And one thing that never made sense to me is, we talk about longitudinal waves. Longitudinal waves are supposed to have particles that move back and forth, going in the same direction that the wave is going. But we always graph our sound waves like this. And it never made sense to me, because I'm like, well, that kind of looks like what a transverse wave would be, because transverse waves go up and down compared to the direction that the sound is moving. What we're actually graphing when we are graphing sound waves like this are the compressions and the rarefactions. So what's really happening when sound waves travel through a body, and I'm going to grab a different pen because that one clearly is running out. When sound waves are actually traveling through the body or through some sort of media, they're causing a particle to either move forward or move backwards. And they kind of start at this neutral position. So you have your particles hanging out, and as that sound wave comes through, it's going to smush those particles really, really close together. And then the sound wave will pass through, and there will be some stretching out of those particles, and then they get really compressed together again. So what we have is a compression and a rarefaction. And so then if we were to graph this, we'd have our compression and our rarefaction, and then our compression again. So when we go back to this graph, this zero line is kind of our neutral position of one of our particles. Our plus is when we have really high density or really high pressure, and our negative is when we have low pressure or low density. Now pressure and density are acoustic variables, which is going to be the next thing that we talk about. But this is just something that gives you a better idea when we get into talking about those variables. We're talking about rarefactions and low acoustic variables and compressions and high acoustic variables. So that was a real big light bulb moment for me with this whole graph thing. I'm surprised it took me as long as it did to figure that out, but I hope it helps you to better understand what this graph of the waveform is really telling us. Now the other couple of words that I have on this board here are for helpful words to know are acoustic propagation properties and biologic effects. So acoustic propagation properties tells us the effect that the medium has on the sound wave. So as a sound wave is traveling through a rock, what does the rock do to the sound wave? That's acoustic propagation property. What does the body do to the sound wave? That's acoustic propagation properties. Again, it's the medium's effect on the sound wave. The opposite of that then is biologic effects. And this is specific to ultrasound and to the body. And this tells us what does sound do to the medium, and in this case, the body, the biological tissue. So what, again, does sound do to the body? Now, the acoustic propagation properties are going to be covered pretty well in this chapter. We're going to talk about how media and sound interact. And then we have another chapter that's like just about that. So we will cover that very well in these first part of the book here. At the end of the book, we talk about intensities, and we talk about quality assurance, and we talk about biological effects. What does sound do to the body? What do we need to do as sonographers to protect our patients from the effects that sound can cause? So just a few terms to kind of get us started in this chapter. Otherwise, let's get going on our acoustic variables. So here they are. Here are those acoustic variables that I was just telling you about. So acoustic variables are things that oscillate or react rhythmically within the sound wave. And if these three things are changing in a sound wave, then we can define that as a sound wave. If anything else is oscillating, then that is not a sound wave. So pressure, density, and distance, any one of these three things that are oscillating, we've got a sound wave on our hands. Now pressure is when those particles become very close to one another and they exude more force in one area. So the definition of pressure is the concentration of force in one area. And we measure that in pascals, often abbreviated down to PA. The second variable is density, and that's going to be mass per unit of volume. So again, when all those particles move together, we have more mass in one area. The density increases because that little sliver, where all those little dots were, that's a heavier spot. We use units of kilograms per centimeters cube, or basically any sort of weight per cubed volume. And then the last part is distance. We know that those molecules move back, or those particles move back and forth in a motion. They travel a distance, and that is a measurable distance. So our units for distance then is any of your basic movements, centimeters, millimeters. So what is sound doing when it travels through the medium? As we had mentioned before, compression and rarefaction are two key words for this traveling. Compression is when everything is squeezed together. Rarefaction is when it is all spread apart. So as sound is traveling in this direction, again, it's going to move these particles really close together, and then that's our up portion of our wave. In our down portion of the wave, those particles become spread out again, and then cyclically or oscillating, those particles will come together again, and that is how the sound propagates through a medium. Now another term that you'll hear for these parts of the wave. This is also known as the peak, and the bottom is known as the trough. So those are some other words that you might hear for those areas. So again, knowing the difference between compression and rarefaction, what's happening to the particles as that sound wave propagates through the medium, will just help you kind of to visualize what's happening. Why are we calling this a higher area of density, or why is this more pressure in this area? That's because more particles are there. I think that just helps to kind of visually think about it that way. And our next chapter is where we're really going to hit these acoustic parameters, but it's a good idea to bring them up now. So remember, we had 3 variables. We have 7 acoustic parameters. So again, 3 variables, pressure, density, and distance, that tell us we have a sound wave because they are acting rhythmically and oscillating. That tells us we have a sound wave. What the acoustic parameters tell us are more details about that sound wave. You can't have acoustic parameters unless you have a sound wave. So the acoustic parameters that we're going to learn about, and this is mostly again next chapter, are period, frequency, wavelength, propagation speed, amplitude, power, and intensity. And we're going to learn lots about these in the next chapter. But these are different ways to describe sound waves. Frequency tells us basically how high is the pitch. When we say something has a high frequency, it's high pitched. We'll learn about amplitude and power and intensity as bignesses of the wave. How intense, how much power is behind a wave? How big is it? How much energy is within that wave? So again, 3 acoustic variables, 7 acoustic parameters. And at the top of the lecture, I did mention that we would talk a little bit more between the difference between transverse waves and longitudinal waves. And I had mentioned that at first I couldn't wrap my mind around. We see a picture like this, and I'm like, well, that's what all of our graphs look like when we're talking about sound waves. How can we be doing longitudinal waves when it looks like a transverse wave? And thankfully we've already discussed that. I hope you're on board with that. But transverse waves, when we define them, they are waves that carry particles perpendicular to the direction the wave is moving. So perpendicular means that something is moving at a 90-degree angle to it. And I remember in my physics class in high school, I remember the teacher pulling out the slinky and doing this motion. They were moving their arm up and down, making the slinky move up and down, like we see in the picture here, but the motion is moving away from the person creating that energy. So again, transverse waves are particles moving up and down, but the wave is moving forward. Longitudinal waves then are going to be particles moving the same direction or parallel to the direction that the wave is moving. So now the slinky is having areas of rarefaction, right? And then it has areas of compression, and then it'll rarefact and compress. The energy is moving back and forth parallel to the direction that the wave is going. Now, something special about waves, when they interact with one another, they're going to do something. So we have in-phase waves and we have out-of-phase waves. So in-phase waves tell us whenever the troughs or the compressions match up exactly, the peaks and the compressions match up exactly, or the rarefactions and the troughs match up exactly, we have waves that are in phase. So the peaks and the troughs need to align exactly. That gives us an in-phase wave. Out-of-phase waves then are when we're just a step off. The waves do not align exactly. And let me point out, these waves have different amplitudes. That's okay. It doesn't matter that they're different sizes in this direction. It matters that their peaks and their troughs line up. So here we have 2 waves that are just off a step. Again, they're different amplitudes, but their peaks, they don't match up. Their troughs don't match up. These are out of phase. They do not match up exactly. And when waves interact with one another, we call it interference. And sometimes interference is constructive, sometimes interference is destructive, or sometimes we get a combination of the two. So when waves interfere with one another and they are in phase, we get constructive interference. Constructive interference means that we're going to add together the power of these waves. So for example, we have a wave here, and here's our wave. And we have a second wave coming through, maybe like this. Now look, our peaks and our troughs all line up. These are in phase. What's going to happen is that these are going to get added together, and what we're going to get in the end is a wave that is a combination of the two. It's much bigger than what we originally had. So in-phase waves construct with one another and make a larger wave that is equal of the two components. Now, destructive interference happens when we have any waves that are out of phase. Now, the example on the page here shows us an example of two waves that are 180 degrees out of phase. That means that they are just going to 100% cancel each other out. But in reality, waves aren't always going to be 180 degrees out of phase. We might have a wave that comes through like this, and we might have a wave then that comes through like this. Oh, that's almost 180. Try that again. All right, we have our wave, and then the next one is just a little bit off. That's a lot harder than you would think. Anyway, so now what's going to happen is that these waves are going to interfere with one another. The particles that are overlapping in these areas are kind of fighting both waves. Which direction do they go? Should I be compressing right now? I don't know. Should I be in rarefaction mode right now? I don't know. And so instead of combining together, they actually subtract from one another. And in the end, we will get a smaller wave than what we originally had. So destructive interference makes waves smaller. And if they are 180 degrees out, then it makes it completely canceled. And lastly, there's a combination that can happen as well. And we're going to see in ultrasound that this is actually most likely what is happening. We're going to have waves of different frequencies coming through. We have different pulsations of waves going through. We have the machine sending out random frequencies to with coded excitation. And so when we have that happen, our waves come out like this. Oftentimes, these are what our pulsed waves look like. There's going to be other things happening through here too. And in the end, Adeline's got a great picture of it. We get kind of these weird, kind of shaky waves on both sides, and it's just filled in through both sides. We just get this combination of deconstruction and constructive interference, and we just get kind of a whole new beast of a wave. So that's mostly what's happening in ultrasound. It's difficult to draw and really conceptualize it. But just know that most of the time we are getting this combination because the waves are striking the media at all different angles and at different times. And that brings us to the end of Chapter 2. So Chapter 3, we're really going to hit the 7 parameters that we mentioned in this chapter.